Hey, this is Tina Subramanian with my second physics lab. So, intro, how does two-dimension kinematics equations predict real-life kinematics experimented by us? And that's the whole point of our experiment. So to get started, we're going to be testing out some key physics concepts. We tested Newton's second law, which states that the force acting of an object is equal to the mass of the object multiplied by its acceleration. This law explains how the velocity of an object changes when it's acted on by a force. In order to do, we use numerous free body diagrams, as well as the equations, such as the ones listed below, which is V average equals RF minus RI over delta T. That's because in the x directions, for one of our models, there was no forces, and then for this one, to calculate the positions, we used this formula just because there were forces acting on the object. So key assumptions made in this experiment were that no air resistance or friction for the first part, so there was no drag. The table is completely flat. In the second part, we assumed only gravity and drag were acting on the object. Well, there may have been more. What we found, overall, the Newton's second law did a good job predicting the position in the real versus computational. However, it's still slightly inaccurate due to errors we'll mention in the coming sections. Methods. To carry out this experiment, we used our arm to create projectile motion, which of paper mass in the plus x and the positive y direction. Using the trapper app, we calibrated the total distance and we were able to track displacement over time. Using the computational software, we measured displacements according to the ideal conditions, and here's the materials we used. So the system was the projectile motion, the surroundings was everything else in the experiment, including the table, gravity, and drag. We put initial force, after that gravity and drag were acting on the object. Models explained, we use our arm to create a projectile motion with a paper ball. Using the tracking software, we were able to track each of the points, and we obtained 11 frames, which lasted 0.337 seconds. Because we have multiple forces acting on the ball, we can use Newton's second law to calculate velocity, and then help that to calculate position. The tracker software calculates the position each of the frame and shows us time as well. And then from this tracker, we were able to use our initial velocity in the x and y for both our models. So in order to find our velocity in the x direction, we used the formula below, which is V average equals RF minus RI over delta T. Just because that there were no forces in the x direction, that means V should be constant throughout the trial. That means V average equals V initial equals V finals. Then for the y direction, we use the formula right here and the right, and then you can see our calculations how, because we had the final position, initial position, gravity, and time, we were able to calculate the initial velocity in the y direction. And then here's the code. You can see that we changed all the time, delta t, the initial position, velocity, and gravity based on our calculations below. And here is the graphs we got. As you can see, velocity in the x direction is constant, velocity in the y direction is linearly decreasing by 9.8 because that's our acceleration. And then the second model, you can see here that we included drag into account, and we showed our calculations here. And it's not as linear, there's some curvature, and yeah. So then we can see our comparisons here. We have time, we have x of the real life model, y of the real life model, x with the computational drag, y with no drag, x with drag, and then y with drag. And I'll explain this more, but you can see that the real life model seems to be going ahead of both the other ones, which was very surprising to me, and we'll explain theirs more in detail later. So yeah, so weirdly in our actual measurements, the position of x and velocity seem to be greater than both the computation models. You'd expect with driving gravity that it would be the furthest behind. We might conclude that some external wind source may be pushing it forward, and when we tossed the mass, it didn't exactly start from zero. So yeah, our calibration system might not be completely accurate, leading to a miscalculation in our average velocity. We might have calculated b wrong. What would happen if gravity didn't exist? How would the experiment change? Instead of tossing in a room of gravity, the room had nothing. Then there would be no gravity acting as another force, so we would have to take that into Newton's second law's equation. If gravity was not a force, then velocity would not change throughout the trial, assuming that there's no drag, and we would have to use the formula Vf equals Vi, and it would be constantly going up and to the right. Final conclusion. It's hard to test Newton's second law due to the many surrounding forces that are apparent in a physics classroom. We can test his ideals on computational software, but it's very hard to do it in an actual experiment. Nevertheless, our results were extremely close, proving that even though there were some forces that might not have been intended, or we didn't intend, his general theory held true in our experiment. So, yeah.